Okay, now we're going to start on the solution for the problem on page 243. Actually, there's two problems. We're doing problem 7 first. The time taken to eat 3 donuts and the person's age is recorded on the table below. They're trying to see if there's a relationship between how fast you can eat 3 donuts and how old you are. So they put the ages of the people on the top row. They put the time that it takes to eat the 3 donuts in the bottom row in seconds. What's the correlation coefficient R for this? I mean, is there a relationship between age and how long it takes to eat donuts? Well, the first thing you're going to do is you're going to do stat edit, because you want to put all these relationships inside your calculator. We're going to do that in lists L3 and L4 because I already used L1 and L2. You could put an L1 and L2 if you want to. So L3 starts out with 8, 12, 15. You can see I've already put in the data. 8, 12, 15. The second row is 23, 21, 17. So you can see that I'm already putting these data into these two rows. Find the correlation coefficient R and comment any results. Correlation coefficient comes out when you do linreg, and you do linreg by doing stat calc and then going down to number 4, linreg. And that'll not only give you the equation of the line, which goes through these points as best as you can, it also gives you the correlation coefficient, which is how well those points fit the line. And so in here you're going to specify L3 and L4 because we didn't put our x's in L1. We didn't put our y's in L2. We put the x's, or the first row, in L3. We put the y's, or the second row, into L4, so we need to change it to L3 and L4. You do that with second and L3, second L4. I already did that. Then we go down to calculate, and we press calculate. And it gives you several lines. The first 3 lines give you the equation, and if you want to write the equation out, it's this one here. It's y equals, and there's 0.215x. I got the 0.215 from here. I rounded the 4 up to a 5 to give 3 significant figures. 14.3 is the b. I rounded the 2 up to a 3. So you can see the a you fill in there, 0.215, x plus 14.3. What is the meaning of the number multiplied times the x? Well, it's the gradient of the line. What is the number of this constant, which is added afterwards, b, 14.3? It is the y-intercept. So that's just, for other problems you need to know that. For this one, maybe not. So that's the equation of the line is b, and it says write down the equation of the regression line. There it is, right there. Actually, part A is asking you for the correlation coefficient, which is R. Here it is, 0.809. But the 9 rounds up to a 0 because of the 5. That gives you 0.810. Comment on the relationship. Comment on the result. Well, if you remember, between 0.75 and 1.0, that would be a strong correlation. Between 0.5 and 0.75, that would be a moderate. 0.25 to 0.5 would be weak, and 0 to 0.25 would be very weak. So 0.810 is a strong positive, and it's positive because it's positive 0.810. If it was negative 0.810, then it would be strong negative. Now r squared is always positive, but r is either positive or negative. Remember that if it's a line that goes diagonally up, then it's a positive correlation, and if it's a line that goes down, it's a negative correlation. Okay, so this would be the comment would be that it's a strong positive correlation. Part C says, use your equation to estimate the time taken by a 40-year-old to eat 3 donuts. Well, all you have to do there is you just, the age of the person is x and the time is y, so you know that the x is 40 in this case because it's 40-year-olds. So you put 40 in for x, you multiply it out, add the 14.3 on your calculator, and you get 22.9. So y equals 22.9. That is the time it takes for a 40-year-old to eat 3 donuts according to this data. Okay. Now, if they ask you something like, now, is the data you have reliable to find the time it takes for a 40-year-old to eat 3 donuts? And you could say yes in this case. Why could you say yes? Because this cloud of points ranges from 8 to the highest point is like 78, right? So you have ages between 8 and 78, which includes 40. In fact, you have some points that are close to 40 also. So yeah, you can reliably predict the amount of time that a 40-year-old can eat 3 donuts, because not only is it a strong correlation, but you also have data points that are very close to 40. So that makes it reliable. Now, what if they said, oh, what about for a 3-month-old baby? Is this data reliable to predict how long it takes a 3-month-old baby to eat 3 donuts? No, because the lowest number you have is 8 years old, and that's very far away from 3 months old. So you cannot really predict the time it takes for people outside of these ages to eat 3 donuts. Okay? All right, now let's move on to the chi-square problem below. Here we are, number 8. 100 people are asked to identify their favorite flavor of ice cream. The results are given in the contingency table, classified by age. So we see across the top we have the age bands, the age ranges, and across the side we have the flavors of the ice cream, vanilla, strawberry, chocolate. You see you have the totals of each category on the bottom and the right. You don't count those in the size of the contingency table. So later when we are figuring out what is the size of the table, we're just going to say it's 3 by 3. Okay? So the first thing they ask you is, okay, perform a chi-square test at the 5% significance level, that's important, 5%, to determine whether the flavor of ice cream is independent of age. State clearly the null and alternative hypothesis, the expected values, and the number of degrees of freedom. Okay, well, some of this we can do without using the calculator, such as the null and alternative hypothesis. That's pretty easy. Okay, the null and the alternative hypothesis, H0 and H1. H0 is the null hypothesis. The favorite flavor is independent of age. Whenever you write a null hypothesis, you always write that the two factors are independent. When you write the alternative hypothesis, then they're not independent. Okay, so you just put the two factors there, favorite flavor, age. Are they independent or not independent? With the null hypothesis, they're independent. With the alternative hypothesis, they are not independent. That's the way it always is. Okay, so now the thing is we need to figure out the degrees of freedom. And the degrees of freedom, you remember, are if you take 1 less than the number of rows and 1 less than the number of columns, so 3 minus 1 times 3 minus 1, it gives you 4. The reason why is 4 of these numbers can be varied freely, and then once you choose 4 of these numbers, then the other remaining numbers must be a certain number according to the totals you have. So that is why they call it degrees of freedom, because you can vary 4 of the 9 numbers. You cannot vary all the numbers. Okay, once you vary those 4 numbers, the remaining 5 numbers are locked into a certain value according to the calculation. Okay, then we need to put this table here that I made a red square around. We need to put that into the calculator, and we use the second matrix to put them in. And so we're going to put them in using the edit function. We're going to put them into matrix A, and then we're going to use matrix B to output the expected values. And so the way you put that in is first you need to say, hey, I'm going to put in a 3 by 3 matrix, so you say 3 by 3. And then we say, okay, well the first one's 14, and the next one's 11, and I'm going to pause here because... Okay, so I just filled in my matrix A with the data from here, right? And then I'm going to run a chi-square test on this data, and the way, let's get out of here, and then we're going to run this chi-square test by doing stat test. Go down to, I think, the next page. I'm going to press the button slowly for the emulator. There it is. Enter. Okay, and so yes, we did put our observed data in A. The expected frequencies are going to come out in B. That's fine. I didn't use B for anything. It's going to overwrite whatever's in there. So calculate. So it gives us the values. 0.604 would be the chi-squared value. I wrote it down here. 0.963 would be the p-value. I write it down there. The degrees of freedom for, I've already calculated that. So now I have that data, and it also wrote in to matrix B the expected values. So I'm going to go look at that. We do that by going to second matrix, and then I go to edit. It's easier with edit because then I can see without scrolling around. You can. Oh, I went into B. I want to get A. I want to get B, not A. So I go second matrix, and then I go to edit, Then I go to B, enter, and then now I get all the values, and I'm going to put them here: 14.1, 10.6, 13.3, 11.8, 8.96, 11.2, 11.1, 8.4, and 10.5. So those are the 9 values here. And then I divide those into categories: less than 25 years old, 25 to 45 years old, above 45 years old, and vanilla, strawberry, chocolate. Okay, so these are the values that I would expect to get if there was no relationship between age and flavor, but what we got are this. And so now, are these values so different than this that we are going to reject the null hypothesis, that they're independent? And we'll do that by looking at the chi-squared value and the p-value. Now, just one thing: if the test asks you, oh, justify that the less than 25-year-olds who like vanilla is 420.1, the way you calculate that is you look at the 38 and you look at the 37, okay, and you say, okay, 38 divided by the total number of people, 100, times 37 divided by the total number of people, 100, times the total number of people, 100, is equal to 14.1. That's how you calculate it. The reason why is because, let's say, this column is 38% of the total. This row is 37% of the total. Now, if everything was totally independent, then you would expect that 37% of these 38% of the people will like vanilla and be less than 25. So you would multiply those two together, and then you would multiply that times the total number of people. Okay, so that's how you get 14.1. You multiply this percentage times this percentage and multiply it times the total number of people, like you did here, if they ask you that. Now that we have the chi-squared value and we have the p-value, do we reject the null hypothesis? Well, remember, chi-squared is proportional to how radical the data is, and 0.604 seems like a small value, so it's probably not radical, which means the numbers are very close to the expected values. If it's close to what's expected, then probably we're not going to reject the null hypothesis. Probably the data is independent. And we would like to compare the chi-squared value to the critical value, but we don't have the critical value because it never gave it to us. Well, we're lucky because you don't have to have the critical value. If you have the p-value, which the calculator always gives you, you can compare the p-value to the significance level, and the significance level is 5%. The p-value is 0.963, which is 96%. Now, the p-value is the opposite of the chi-squared. The chi-squared you reject when it's big. The p-value you reject when it's small. Well, in this case, the p-value is much bigger than the significance level, so you do not reject. Okay, so you accept the null hypothesis because 0.963 is much bigger than 5%. 5%, remember, is 0.05. Okay, so that could be very confusing. You need to remember that chi-squared big means you reject. P-value small means that you reject. Okay, so they're the opposite. When p-value is big, then you accept the null hypothesis, like here. If they don't give you the critical value, the only thing you can do is use the significance level. Now, don't get confused and start comparing chi-squared with the significance level, and that kind of shows that you didn't really understand what was going on. So make sure that you always compare chi-squared to the critical value. If they give it, compare the p-value to the significance level. Okay. And just to show you the screen again, we'll do stat, tests, and then we'll do calculate. And then just to show you, they always give you the p-value and the chi-squared. So even if they don't give you the critical value, you can still find it with the p-value. Okay, and so the next problem, which is the page 322 problem, we'll put in the next video.